Hello, everyone. Welcome to Pre-Lecture 5. This is going to be for Lecture 5. And so just a reminder, this material will not be on quiz number 2, but it is fair game for quiz number 3 the following week. So we're getting into a new chapter here and coming out of talking about intermolecular forces and starting to talk about solutions. And so in General Chemistry 1, solutions were defined as a homogeneous mixture of two or more substances. However, we want to add a little more vocabulary this semester. And so the two or more substances can be a majority and a minority component. The majority is going to be called our solvent, and the minority component is going to be called a solute. Okay. So for example, if we have a solid, say salt or sugar, and it dissolves in water, the molecules of the solute then become uniformly distributed amongst the solvent molecules of water in order to form a solution. So an example here of how we would write that, how we would describe that chemically. Say we have sugar, sucrose here as a solid, and we dissolve it in water. All that changes is its phase, right? It goes from being a solid to being dissolved in water, which we designate with this AQ symbol, okay? So it's technically a sort of phase change, but it can be any sort of phase, doesn't have to start as a solid. And when it dissolves, it is then represented with the designation AQ, okay? Most of the time, particularly in Gen Chem 2, our solvent is going to be water, but it can be a ton of different things. And so again, as a general rule, it will be water, but it can be a lot, okay? So some examples of different solutions that are a little bit more exotic are alloys are an example. So this is a solid-solid solution where one metal is dissolved in another. An example of that is the US 5-cent coin, aka a nickel, but it is actually an alloy of the metal nickel dissolved in the metal copper. Air, the air that we're breathing right now, is also a homogeneous mixture of nitrogen, oxygen, and several other gases. And that is an example of a solution. Oxygen, alcohol, sugar, all dissolved in water. Basically, we have different examples here. So any sort of soft drink has CO2 dissolved in it. That's what gives things carbonation. And we have just a number of different examples here. Okay. So these are characteristics of solutions. I will let you read these on your own time. I think they are relatively straightforward and hopefully a review from General Chemistry 1, but it's not something I'm going to focus on in this pre-lecture video, okay? So if we think about how solutions form, they will form through a spontaneous process. And what does that mean? It means that the dissolution or the dissolving of something is not going to require energy input from an outside source. And so in this example, we have two gases, helium and argon. They're separated by a valve. When we turn that valve, they spontaneously mix, right? Some of the helium will go over to this chamber, some of the argon goes over to this chamber until there is a uniform distribution, okay? So if we think about a solvent and a solute coming together, oftentimes this is a liquid. And so in order to do this, we have to put energy in as our first step. So say we start with our solute here in blue and our solvent in red. Basically, the first step is to put energy in to break those intermolecular forces. So this is some sort of energy input. And then when we put the solute and the solvent together, we form new bonds. And so this will release energy. And so this second step basically would be, or step 3 as it's labeled here, is an exothermic process. And so as long as this third step, essentially the mixing of our solute and solvent, releases more energy than it takes to break the intermolecular bonds between our solute and a solvent, then our solution will form. However, if our solute and solvent are not capable of interacting, so for example, if they don't have similar intermolecular forces, then in all likelihood, they won't actually form a solution because the energy payoff will not be there, Okay. So within solutions, one of the primary things we care about is how soluble something is. And so what that means, the solubility of a solute is in a particular solution is the maximum concentration that can be achieved under given conditions. Typically, we mean temperature and pressure there when the dissolution process is at equilibrium. Okay. And so we can designate things different ways. The three primary ways we designate a solution is it's either said to be saturated, and that is when the solute's concentration is equal to its solubility in the solution. If the solute's concentration is less than its maximum solubility, then the solution is said to be unsaturated. Then the one that tends to trip people up most is supersaturation. And this can occur when the solute exceeds its maximum solubility, but it exists in a non-equilibrium state. And so I will tell you, anytime we have supersaturation, that exists generally when we have changes in temperature or pressure. Okay, so those are the situations where you're going to have supersaturation occur. And a common example of that is going to be, say we have a soft drink, some sort of carbonated beverage, and we open it, we hear some gas come out as we pop open a can of soda, or for example. But as long as it's carbonated, it has not gone flat, and any sort of carbonated beverage is going to be supersaturated with carbon dioxide. However, given time, it will eventually reach equilibrium, and the CO2 concentration will decrease until its maximum solubility is reached and the solution becomes just saturated with CO2 instead of supersaturated. Okay. One other thing, another concept we're going to talk about with regards to solutions are electrolytes. And so when some things dissolve in water, they form ions. And these are important class of compounds called electrolytes. Things that don't dissolve in water to separate to form charges, we would call non-electrolytes. And so essentially, when we have an electrolyte, we're asking the question, when this dissolves, does it produce ions? Okay. So example, we have ethanol, which is a covalent compound that does not dissociate really at all when it's dissolved in water, so we would call that a non-electrolyte. We have potassium chloride, kind of a classic ionic compound that will fully dissociate, and so that is an electrolyte. Part of the reason we call it an electrolyte is because it will then conduct electricity, as shown by our light bulb here. And we can also have things that are weak electrolytes, and so things that partially ionize in solution. So an example of that would be acetic acid that only partially ionizes, and so we would be able to conduct a little bit of electricity, but not very much at all relative to our full electrolyte. Okay. Also, just a reminder that electrolytes are what plants crave. I'd recommend clicking on that link to watch a video that I find quite funny if you haven't ever seen the movie Idiocracy. Okay. So what does dissolving electrolytes actually look like? It actually takes us back to intermolecular forces, where when we dissolve something, so we have these red and white water molecules here, they're going to interact with our ions as it dissolves. And so they will cause a favorable energetic interaction where we have the positive part of our water interacting with the negatively charged chloride. We have the negative part of our water, if we were to draw a dipole on it, interacting with the positive part of our K+ or potassium, right? And because those are favorable ion dipole interactions, this ultimately leads to the salt dissolving to form a conductive solution. Okay. Pure water, pardon me, is a poor conductor because water is a covalent molecule. Hopefully we remember that from Gen Chem 1, but it is good at dissolving things that are electrolytes. However, it can also dissolve things that are non-electrolytes, such as nitrogen gas or sugar, and those are going to be poor conductors or poor electrolytes as well. Okay. That's it for the pre-lecture. If you have any questions, please let me know. Otherwise, I will see you in class. Take care.